Greetings, geologists, for the last period of the Paleozoic. Yay! It's been a journey, hasn't it? We started with our small little shelly animals at the bottom of the Cambrian, actually worm burrows, that marks the beginning of the Cambrian, and we had the Cambrian explosion. Then in the Ordovician, we saw the massive Tippecanoe and the building of new organisms like bryozoans. Silurian, we saw the Tippecanoe at its peak, and it produced all those evaporite deposits and massive coral reefs. We hit the repeat button in the Devonian, as the Kaskaskia did the same thing. We ended up with some really important rock layers from the Devonian that represented the collision of Europe to North America, like the old red sandstone in Europe and our Catskill red beds, and of course at the tail end of the Devonian, the Chattanooga Shale. In the Mississippian, we saw a remarkable time of carbonate deposition that laid down thick sequences of limestones just cluttered with crinoidal stems and bryozoan fragments. Then we would enter into the Pennsylvanian period, where we had just evolved our first reptile in the Mississippian, our first amphibian back in the Devonian, and things would get even stranger with the Carboniferous, specifically the Pennsylvanian swamps and the giant insects and the massive mountain building from South America and Africa colliding with our continent. So that sets the stage for the Permian. It's all a storyboard, so when you're studying for your quizzes and exams, you need to think about it as a history lesson, because that's what historical geology is. So you may be looking at this rock wondering, wonder why that's there. We're talking about Pangea, at least I thought we were. First of all, you need to recognize that this rock is infamous for the Permian period. It is a remarkable coral reef, which is very rare circumstance for the Permian period in North America, pretty much anywhere in the world, because as Pangea assembled, we would have had a remarkable change in climate. So we'll come back to this as a little hooker there in terms of making you want to keep watch. I'm going to tell you that this is El Capitan Reef, and it's something special, and it's famous for a place that may surprise you. All right, let's talk about the changes of the Permian period. The Permian lasted from 299 million years ago to 251 million years ago and is called the Age of Pangea. Pangea was assembled during the Permian period, but that's not the only reason it's famous. In terms of what we have in the United States, the Permian period provided us with an ample source of fossil fuels, in particular oil and gas. While coal was famous for the Pennsylvanian, petroleum products came out of the Permian period. That rock I just showed you at the beginning as a hint towards that. So most of North America is not going to be submerged under a continental sea of the Arb-Soroka. It's going to be dry and arid. Let's talk about why. If you can see, as Pangea is sutured together, we should have mountains building anywhere you see these continents colliding, and they should be similar to the Himalayas today. So that's going to cause some dramatic climate shifts. Couple of things to consider as we go through this. The first would be this giant ocean that we have that surrounds all of Gondwana and Laurentia. This thing over here, which is the global ocean, these are smaller seas that will become important during the Mesozoic. Panthalasset is sometimes called the Panthalastic Sea, is the big global sea during Pangea time frame. This is significant because the water in the oceans for currents would have freely been able to circulate, leading to a very warm climate to begin with. The second part to that is the mountains that stand everywhere in the interior parts of the continent are going to lead to a drying effect in the middle of the Pangean continent. We can't talk about the supercontinent of Pangaea as if it was only made up by big giant continental plates. There are numerous microplates, small plates. For example, today, small plates might be something like Juan de Fuca out on the Washington State and Oregon and Northern California boundary. These small subduction zones were critical for bringing the plates together. Many of them sutured on as land masses, others ripped it off and went elsewhere. Some were subducted completely and consumed at subduction zones. Nevertheless, they play a huge role in assembling the supercontinent known as Pangaea. This discussion about climate is especially important in the Permian because the climate had some hurdles to overcome. And I think about the most famous rain shadow desert currently in the United States, and that would be Death Valley. So here's kind of what happens. I'd like to put Death Valley, but put it on an order of magnitude like the Himalayas. And this certainly happens in the Himalayas as well, and in the Andes, which is in South America. The mountains that are facing the ocean act as a barrier, a topographic barrier. So what will happen is, as the rising air mass goes up this mountain, it reaches its dew point from adiabatic lapse rate. That's a very large set of words that's actually an earth science term and meteorological term. But essentially what that means is for every 1,000 feet you go up, it cools by a certain amount of temperature, eventually reaching a dew point. And when the dew point's reached, the air mass will release its water. So the seaward side of these mountains tends to be very green, tends to have subtropical, certainly not arid or semi-arid conditions. However, the clouds rarely make it over the tops of these mountains, especially when you're talking about something that's Himalayan in size. That means the interior side, which would be this side over here, is going to have any air that makes it over would be extremely dry. So the vegetation, the organisms, the animals, the plants, all of these things that would be on the other side of these mountains, if they're living there, they're going to have to adapt to some pretty significant semi-arid and arid conditions. I would say think about the Mojave Desert. Think about the Sonoran Desert that we have in the United States and North America. And think about how hot those places are and how dry they are, and then magnify that substantially, and that's likely what was happening during Pangaea time frame. So we know that this happened not just because we're hypothesizing because of rain shadow conditions today. We have some rock evidence, and the rock evidence comes from red beds that we find in extensive evaporite deposits that are actually used for economic gain. So let's take a look at the Permian paleogeographic map, and let's take a look at where the Absaroka was and where it was not. I think it's so important to point out that here was our last uplift of the Appalachian that occurred in the Pennsylvanian. Here is your Ouachita-Orogeny, which plays a role in what we're fixing to look at. And then here are a series of highlands left over from the Antler Highlands. And here what's left of your ancestral Rockies, which will be wearing down and eroding down to nothing, only to be uplifted again by the end of the Paleozoic. What I'd like to focus in is this area right in here. Kind of makes a horseshoe shape right here. That's a complex reef system, coral reef type system made out of algal and coral reef deposits. Here's what's so important, and including bryozoans, I shouldn't leave them out, and even brachiopods. This area is going to be the key component of why we have so much oil and gas deposits in West Texas and far east New Mexico. It's responsible for the Permian Basin, which we'll be looking at in just a few moments. So these reef platforms would have been shallow marine areas that built up towards the surface of the ocean, and they created this massive coral reef known as El Capitan, and it filled up these areas that were the lower basin areas, which we'll get to shortly, and those are where all the small microscopic animals died. And it's in the basins that we find all of this remarkable oil and gas that's Permian in age. So what is the Permian Basin and why do we care? A lot of the oil and gas that services the United States comes from this particular area. Of course, the Gulf of Mexico is another big area, and so is Alaska. But down in terms of being on land, this was easy to get to. And starting around the 70s, people started walking out into their ranches only to step into black ooze, which turned into being black gold, known as oil. So how did it get there? So let's take a look at the dynamics, then I'll kind of describe to you the significance. The blue areas that you see right here are going to be the shallow continental shelf. In other words, they're going to be the areas where the coral reefs are going to grow. And each of these basins, like Delaware Basin, Midland Basin, Valverde Basin, these are going to be the sections that are going to have all the deeper areas. They're indentions in the ground, so they're going to be low-lying areas. They'll be deeper, and as the microscopic organisms that were living in these areas migrate out to the sea top here and they die, they'll sink down to the bottom. That's important to note because they're going to die and make mass accumulations of what we call hydrocarbons. And we'll get to how we make hydrocarbons shortly. The Permian Basin was one of the few areas of the North American craton that still had coverage from the Arab-Sirocco Sea, making it very unique. Parts of Canada did, parts of the western United States did, but we have extensive benefits from this particular period that the rest of those areas would have loved to have had. The special relationship that existed between the platform barrier reefs and open ocean shelf areas played this dynamic relationship that produced us incredible petroleum reserves. If you went out to West Texas, this is what you would see. And keep in mind the area of Midland and Odessa is flat as a pancake, and you'll drive for hours, or if you've flown over it, you see these pump jacks going nonstop, and they're everywhere. And it's almost overwhelming when you realize how much oil is still in existence in the Permian Basin, even today, after all these decades of utilizing it. How does crude oil and natural gas form? A little short lesson here is worthy to note, and I'll go back to the importance of things like microscopic foraminifera, radiolarians, diatoms, things that are tiny little microscopic organisms that contain a small amount of this oil product while they're alive as their food resource. So oil and natural gas are formed by the burial of organism substances in anaerobic conditions. Well, we visited anaerobic when we were looking at the Chattanooga Shale in the Devonian. So this can happen in ocean or lakes, but nevertheless, most of the time we make oil and gas deposits out in ocean basins. As these dead animals, little microscopic animals, accumulate in mass quantities at the bottom of an ocean, or a lake for that matter, the temperature in the organic rock layers over time can create crude oil. If you continue to heat those rocks up, you can vaporize the hydrocarbons, turning them into natural gas. So the animals are living, they die, they get buried, and then here we are in modern time utilizing these as hydrocarbon deposits. Not every dead animal layer is going to produce hydrocarbons. A number of key factors need to be in place. And one I can think of is how do you keep it from seeping out? That's where the value of anticlines and synclines and then faults can even help bring them to the surface. And that's certainly what happened with Texas in terms of having some continental and cratonic stresses happen during the Cenozoic that would crack up some of these rocks that would allow some of this material to start surfacing on its own as seeps. This brings me to a very, very important rock layer for the Permian, El Capitan Reef. So there are a number of El Capitan formations. This is not the only one. I can think of Yosemite would be an example, and people confuse this with that. Don't. This is not granite, first of all. This is a gigantic thick sequence of limestone reefal material. To be exact, it was the horseshoe area that was the platform reefs that I showed you a few minutes ago on the diagram. These giant limestone layers were converted into limestone well after the Permian period was complete, and literally, folks, there are over 10,000 feet of it. It is a just phenomenally thick unit, and this unit contains fossils that were indicative of marine depositional environments at that time. About 20 million years ago, the region was faulted and had active fault movement. We'll learn why later in the semester during the Cenozoic. But to make us long story short, this fracturing and faulting that was active caused the limestone to be cracked up, which opened the potential for some of these dead organisms that were in the bottom of these rock layers to start changing their form. And they became hydrogen sulfide, for a better lack of words. They became sulfuric acid. And as they built into these structures underground, stories of beneath your shoes, 50 to 70 stories beneath your shoes, they hollowed out a really famous cavern known as Carlsbad Caverns. So this is how Carlsbad got born. It got born on those platform reefs that make up El Capitan. So if you get the chance to go to Carlsbad, take the hike down. You have to get there about 1:30 to 2 p.m. and they're on mountain time, not on central time. And allow yourself more time than the average person to go down. I would take a headlamp so your hands are free to photograph. And I would look at the walls as you're walking down, because you're going to see some infamous marine fossils like fusulinids, bryozoans, mollusks, spiny brachiopods. You might get lucky and see a trilobite here or there, a remaining crinoid. So these animals are just all over the limestone because they represented this phenomenal coral reef. The story of Carlsbad actually happens in a stage story. The first stage is the formation of El Capitan Reef in the Permian. The second is the 20 million year ago uplift of the area and faulting of the area that allowed cracks to form. And then we have the water that gets into the cavern itself once the cavern is made. So realize that the law of cross-cutting relationships applies here, because a cavern has to be younger than what it crosses over. In the case of Carlsbad, it was carved out by dead organisms that produced a sulfuric-based acid that ate away the fabric of the limestone, unlike what most of Texas experienced, which is carbonic acid. When you go to Carlsbad, literally it's more than 50 stories beneath your shoes. So it's a long way down there, and this actually, the cavern creation happened about 20 million years ago, and then another phase occurred. As the cavern began to get wet, it created cavern decorations. So you're looking at the rock formation process first. The second stage is the cavern development, and the third stage would be the cavern decorations, which are in modern geologic time. So Carlsbad Caverns wouldn't be there had it not been for the Permian Arb-Soroka Sea that just happened to be in West Texas and eastern New Mexico during that time frame. When I took this shot at Carlsbad, I'm in love with totem poles. I just think they're just really awesome, and that's one of the big totem poles from the big room in Carlsbad Caverns. And you look at it, you realize when you're in there how small we are as humans and how long these things have been forming. These are cavern decorations. There's stalactites, stalagmites, there's soda straws, there's popcorn, there's cave pearls, there's stalactites, the totem poles I just showed you right here. But nevertheless, the cave has active cavern decorations that you can go see and experience and see how a cavern has been made. Keep in mind, this is Permian in age, so it's pretty remarkable that we could get a cavern this deep down, so there must be a story there. This is a stalactite and a stalagmite that have almost married. This is a good indication of how the tips are sharp at stalactites and you get rounded mounds for stalagmites. But one of the many cavern decorations that you can see in Carlsbad Caverns. While you're in the area, if you're passing back into Texas, you'll drive right through the Guadalupe National Park. It's a very nicely kept secret of the national park system. It's a very interesting place because it has a number of Paleozoic aged rock layers exposed in the area. One of the most noticeable are Permian evaporites, which are in the form of salt flats, which is exactly what you're seeing in this photograph. So as the Arab-Soroka Sea would rise and fall, the areas known as the Permian Basin would sometimes be wet, sometimes they wouldn't, depending on how close to the shoreline they were. These areas developed extensive evaporite flats known as halite or salt flats. Guadalupe National Park has just a plethora of them that you can see as you drive through or hike through the park. If I'm going to talk about the Permian Period rock layers, I can't just talk about El Capitan Reef. I need to talk about some of the famous layers of the Southwest. We'll start with the Coconino Sandstone, which is known or named after the Coconino Plateau region that's up in Arizona. So if you go to the Grand Canyon, you can hike from the North Rim down to the Coconino Overlook. We go there every year on field course and we have class right on that ledge that you're seeing. I teach right there. We talk about the different rock layers and how they're made. And it's really awesome. It's not a very long hike to get to this point. This is nowhere near the bottom, so it's really close to the top. What's important about the Coconino is a few facts that will take you back to physical. First is it's heavily cross-bedded. So you know from your physical days that that means that it had to have been deposited in an Aeolian desert environment. High-angle crossbeds are the key to recognizing most desert-based sand dune deposits. And I said most, and we'll talk about an exception here in a minute. The other key thing that I would note about the Coconino is that it has something unique about it. It's a beautiful color, first of all. It's the rock layer I have pointed over here, and I'll show you some shots of it from Sedona. It's also in that area, and it's very noticeable. It's towards the top of the Sedona landscape that you'll see there. But in the Grand Canyon, it makes a very notable cliff. One of my questions to you is why? Why would the cliff faces be up and down as compared to maybe this rock layer right here that makes a bed that isn't straight up and down? Well, it has to do with differential weatherings. What I'm asking is, does it have a high or low differential weathering for the Coconino Sandstone? If you answered low, you are correct. It doesn't weather very fast, and that's what makes up the cliff faces of the Grand Canyon, and the slope faces are made by rock layers that have a higher differential weathering capacity. This is a good look at the cross bedding. You can see it very well where I put a marker there. This is a highly cross-bedded sandstone. Another way you can determine if you're looking at desert sand dunes versus beach sand dunes is by actually looking under magnification at the sand grains themselves. If you see frosted sand grains, it indicates an Aeolian environment. Here's how. Frosted quartz grains, if you've all seen quartz from lab in physical, and you saw a picture of quartz in our Pennsylvanian lesson about the Ouachita orogeny. So imagine that they're marbles and you smash them together. Probably as a kid you had some clear marbles that you smashed together and they kind of got dull and frosted looking. The same thing happens to quartz crystals when they are blown together in a wind Aeolian environment. There's nothing to cushion or lubricate the grains from smashing together. Instead, in a beach environment, the water acts as that lubricant and actually keeps it from getting frosted. So we can look at the grains under the microscope of a sandstone to determine what kind of depositional environment they were actually made in. So another famous rock formation in Sedona, but I might add it's missing in the Grand Canyon but can be found in other areas nearby, is the Schnebly Hill. So the Schnebly Hill is actually named after this guy, and if you're going to do one of my assignments, you're going to have to learn the story, so get ready. You're going to have something fun to learn about. This is an important rock layer because it makes up almost all of the Sedona rock formations. While the Coconino's at the top and the Hermit Shale's at the bottom, we got this thick unit called the Schnebly Hill that makes up this looking type rock right here. I would say all of this is Schnebly Hill. The top of it is Coconino. This is all Schnebly Hill, Schnebly Hill. The question is, which member of the Schnebly Hill is it? So the Schnebly is divided into 3 different formations, and the one that's the most notable is the Bell Rock member. Then there's above that, there's a limestone unit called the Fort Apache, and then above that, the Sycamore Pass. So important for you to realize, if I got limestone sandwiched right in the middle of this Schnebly Hill, something must have happened to sea level at that time during the Permian period, making it shoreline property in Arizona, right? So how do I really know that the Schnebly Hill, let's say the Bell Rock Formation in particular, is Aeolian and it's not beach? It's inland sand dunes. The difference between inland sand dunes and beach dunes is quite simple. Inland are inside the continent. So this would have been some of the Pangea sand dunes that had formed as the ancestral Rockies were eroding down, receiving their sediments. Bell Rock is smooth. It doesn't have cross beds in it. That's fascinating. So how do we really know it was Aeolian inland sand dunes? We know it because of the frosted sand grains. So the story in the little exercise you're going to have to do, the virtual field trip, will explain all the reasons why, and I'll leave that for a discovery moment as you get there. But know the Schnebly Hill is smooth and doesn't show indications of cross-bedding, but it used to be. I'll put that out there. So it's kind of a fascinating set of circumstances where it was the inland dunes of the dry interior sections of the continent when Pangea was in place. In the Schnebly Hill, this is the Bell Rock member right here. I've got field course students on a hike where we go to Cathedral Rock. We also hike to Bell Rock, which was this particular thing I had pointing that looks like a bell. But this one we hiked to look at some really cool ripple marks, and the Bell Rock member is full of them, which is an indication of being in a unique depositional environment to create that. So we would have some kind of flash flooding in a dry creek bed, like a dry wash out in the desert, and then it would create ripples and it would dry up, and then we would start back with the production of sand dunes. And keep in mind that the Bell Rock is not cross-bedded. I think this is a good place to take a break, and we'll come back and talk about marine life forms from the Permian and terrestrial life forms, and we'll come back and discuss the plants, and then of course the finale of the Paleozoic, which is the mass extinction event at the end of the Permian. So see you back in a little bit, take a break, and bye.